Let's talk about entailment and validity in truth trees for predicate logic. Now, nothing has really changed since propositional logic, but because we have four new rules, we might as well do some practice with those. So as a reminder, if A entails B, that means if A is true, then B must be true. So one of the very common arguments you always get is if you have for all x, px arrow qx, then if you have something like PA, that would entail that you get QA. So this is like all men are mortals, Socrates is a man, therefore Socrates is mortal. But when we have something like this, we can actually rephrase this as an argument, sort of like just what I said out loud. So saying that A entails B is really the same thing as saying that an argument is valid. So for example, all x, px arrow qx, and then you have PA, therefore we know that QA. So these two are equivalent in nature. So if we want to prove that A entails B, or if an argument is valid with a truth tree, we have to remember one special step, and that is when we set up our truth tree for entailment, so all x, px arrow qx, that can be, say, the first entry, the first assumption, we have PA, we need to negate our conclusion. And that is because if A is true, B must be true. So what we're doing for entailment is we're going to hope that everything closes, and if everything closes, we've shown that we need to have A true, and if A is true, we cannot have B false. So that would show entailment, because what that means is if we can't have A true and B false, this means that, oh, B must be true, therefore we have entailment. So let's just see how we can do this with truth trees with three examples. So the first one, and I'm not going to do as much labeling in these, it's more to show the process, and then hopefully, depending on whatever labels your textbook uses or your course uses, you can actually just understand what those are based on your requirements. So I just want to illustrate how these work, just because these get quite big. So for all x, if px, then qx. For all x, if rx, then qx. Therefore, for all x, if px or rx, we get qx. Okay, so to set this up, we put down our two premises, 1 and 2, and then for 3, our conclusion, we negate it. So we have to negate it for our truth tree. Now, because we have negation, this means we're going to be using our rules not for all decomposition and not existential decomposition quite a bit. I mean, in every single proof, you'll need it because you're negating a conclusion here. So that's what we're going to do first. We're going to do negation on 3. So we're going to get exists in x, and it's really important that we put the negation outside of the bracket. So we'll get px or rx, arrow qx, and then we can check off the previous step. So I'll write some of these down, but I will not write all of these down. Okay, now we have premises 1 and 2, and we have an exists x. So what we're going to do is when we have the choice between for all x and exists x, I always recommend choosing a variable first for the existential x. So I'm going to choose, say, a, and we'll do existential elimination. So let's do not, in order to keep that not outside the brackets, PA or should be RA, arrow QA. So we haven't used A yet, and there's no other constants in here, so why not just use that? Okay, so what we'll do now is we're going to break this down further. So we'll do the not arrow rule. So this means that what we're going to get in lines 6 and 7 is we'll get PA or RA, and then we'll also get not QA. And both of these are just negation on the arrow, and that would be the elimination of it. So we can check this off because we're done with it, and we can also check off 4 because we're finished with that as well. Okay, for 6, I also want to split this up because we have PA or RA, so let's do one branch with PA and one branch with RA. Okay, so everything's done except for our two premises. Now the reason I've done this is because hopefully we can get insight into what we need. So we could look for, say, a not PA to close this. We could look for, say, a not RA to close this, or we could look for a QA to close what's coming from 7. Okay, so for 1, for all x, px, arrow, qx, I'm going to put this, and I'm going to do universal elimination with this branch on the left. And we're supposed to put it everywhere, so I will. But for example, let's say, okay, we have PA, arrow, QA. And I should repeat this over on the right since it should go for all branches. I don't think I'll need it, but I'll do it anyway. Okay, so this is uh, for all elimination from 1. Okay, I might as well do 2 as well since we're here, why not? So let's do RA, arrow, QA, and I'm mainly doing it for this right side because I want to get QA on the right eventually. So if I was doing a proof, that's what I want to do. But we'll see in truth trees how that can help. Okay. So now we have the arrow, which means we can do some arrow elimination here, which means we're going to get some branching paths, and we're going to choose which ones we do very carefully. So I'm really only going to break down PA, arrow, QA on the left. So I want to do, split into 2 branches, we'll get not PA and then QA, since PA, arrow, QA is true if PA is false or QA is true. And at this point, we can see that this left branch closes since we have not PA and PA. That's a contradiction. And the right branch also closes because we have QA and not QA. Okay, on the right side, we're going to do something very similar, but this time we'll do it with RA arrow QA, mainly because we have RA up here. So that's probably going to be useful. So we'll break this down into not RA and then QA. And we end up with the same result. So both of these branches close because we have not RA and RA, and we have not QA and QA. So because everything has closed, we know now that this argument up here is valid. If the 2 premises are true, so if this is true and this is true, we've shown that this last conclusion cannot be false, therefore it must be true, so we have a valid argument. We could also say that the first 2 woofs here entail the third woof. That would be another way of paraphrasing this. Okay, let's do another example. For all y, hy, and jyy and my entails or says that there exists an x, jxb, and for all x, mx. Okay, so what we do is we negate our conclusion. And this one, we have to be very careful because we have a conjunction of 2 well-formed formulas here, and we put brackets around the entire thing first and negate that. Otherwise, we would just end up negating the existential, which isn't what we want. We want to negate both the existential and the universal. So what this means for our first step is that we can't do negated existential decomposition. Instead, what we have to do is the rule for not and. And if you remember the rule for not and, this means that we go into 2 branching paths. One would be there does not exist an x such that jxb, and on the right side, not for all x, mx. So it turns it into not a or not b. So we'll put this down. Well, these really shouldn't say 4, this should say 3. And I will write this one down. So this is not and elimination. Okay, now for each of these, we can do decomposition. So we can now push the arrow through. So we're going to get for all x, not jxb on the left, and we'll get exists in x such that not mx on the right. Okay, so this is our not for all decomposition and not existential decomposition. Okay, what now? Well, what I see on the right is an exists in x, so I'm just going to pick some variable for it. So I'm going to say not ma here. So this is existential elimination. Now, my goal on this branch is to eventually get an ma. And for my thing on the left, I'm not quite sure what I want yet. But what I will do is now I will apply the rule for 1. I will do for all elimination, and the nice thing is that we don't have to pick the same variable for both sides. So for the right side, I'm going to pick HA and JAA and MA. But for the left side, I have something with B in it. So I don't want to pick A when I do universal elimination on 1. Instead, I'm going to pick B because I'll get something more similar to what I have. So I'm going to do HB and JBB and MB. So this is fine. We can pick different variables for different branches because these are different branches. Okay, so now we got to do some boring stuff. We got to like break all these apart. So don't need to draw a line there, but I need to do one with HB, then one with JBB and MB, and then break this up into JBB and MB. So uh, those get completed. And on the right, I have to do the same thing, HA, JAA, and MA. Then I'll get one with JAA and one with MA. So this is complete, this is complete, this is complete, and this is complete. Okay, so everything on the right side is complete, and we get our contradiction finally. We get MA and not MA, so our right side is closed. But on our left side, we still haven't had closure yet. We still have for all x not jxb to do. So in other words, I need to replace this x with a constant, and I see I have jbb, so I'm going to replace this with the b as well. So I'll get not jbb by doing universal elimination on 4. And now what happens is I get a contradiction with JBB and not JBB, so this closes as well. And now we can say this argument is valid. Okay, so we close both branches, and the thing I wanted to really show you in this was that when you do universal substitution or universal elimination, you do not have to use the same variable for both sides. So as we can see here, I used B for the left branch and A for the right branch because that's what I needed in each branch. Now, for the last one, for all x for all y, if lxy then kxy, entails that for all x all y, if lxy, then you get kxy and kyx. Okay, so this one is a lot more of a toughie. So let's see what we can do with this. We're just going to go through this systematically. So the first thing we're going to do is we're going to do not all decomposition. So we're going to get exists in x. And now we have to be careful that we negate the entire thing. So this is for all y, lxy, then we get axy and kyx. So I will write not all decomposition for the first one, so that's done. And now in line 4, we're going to do the same thing. Well, we actually can't do the same thing yet because we have this existential out front. So we need to choose a letter for exists in x. So I'm just going to do A, because that's the first one we have, and we haven't used A yet. So we're going to get not for all y. Actually, I don't need to put the left bracket out there anymore. So x is going to be replaced with A. L-A-Y, arrow, K-A-Y, and K-Y-A. So this was existential elimination. Good, that one's done. Now for line 5, let's change colors. Let's do not all decomposition again. So we're going to push that negation through. So we'll get exists a y such that not L-A-Y, arrow K-A-Y, and K-Y-A. Okay, this means that in 6, we're going to have to do another substitution, but we cannot use A, so let's just use B for existential elimination. So we'll get, it is not the case that if LAB, then KAB and ABA. Okay, so we still haven't even used our first premise yet, but let's break this down as much as we can. Okay, which means that in line 7, we have a negation and an arrow, so we're going to do not arrow elimination, which we've seen before in this video already. So this means we'll get LAB, and we'll get not KAB and KBA. This is where I'm going to stop numbering things. I guess I can label this as 8. Okay. This is also not arrow elimination. Now, if we keep going, I want to do not and elimination on not KAB and KBA, just so we can break this up as much as possible, which means we're either going to get not KAB or we're going to get not KBA. So this is not and elimination. Okay, now we have some things we can work with. We have not KAB, we have not KBA, and we have LAB. So we just need to find the negation of one of those. So here's what I'm thinking. The best way that we could do this is if we were to get not LAB on both sides. Because if we could do that, then it's going to contradict with this up here. And that will give us a very easy closure on both sides. If we don't do that, we have to get a KAB on the left and we have to get a KAB on the right, and that just might be a little bit too much work. So I'm going to try the first strategy, and if it doesn't work, we'll try the other strategy. So I want to get not LAB on both sides. So from 1, we're doing 1 now, we're going to do universal elimination on the x, and we can use variables we've used before. So I'm going to put a in for x. So we're going to end up with, on both sides, is for all y, LAY, then KAY. Okay. And what's nice about this is it looks like we're going to get what we want here. But on the right side, I'm actually a little bit concerned, because if we do the same thing now, for all y, LAY, arrow, KAY, we're going to be able to close one side, but I don't know if we're going to be able to close the other. But anyways, let's just do this and see what happens. Okay, so that's universal elimination. And what I should say, my worries here, just to illustrate them a little bit more clearly too, is that if we were to do something else and substitute, say, B, we get LBY, arrow KBY. Now this looks very good for the right side, but we have an LBY on the left that doesn't look like it's going to close. So this is my worry with this one. If we were to do something different, we wouldn't get anything either. So maybe this is not a valid argument. This is what I'm thinking right now. Okay, so 1 is now done. All we have to work with is now 10. So, okay, in line 11, we're going to do another universal elimination. So for the left side, I want to get LAB. So I'm going to get LAB, arrow KAB. And on the right side, I want to get the same thing. Let's just do the same argument and see what happens. LAB, arrow KAB. Okay, now for each of these sides, it's an arrow, so we end up with more branching paths, and this is where the problem is going to come in. So using arrow elimination, we'll get not LAB or KAB, and on the right, we're going to get not LAB or KAB. Now, some things close here, which is nice. First of all, the not LAB branch closes because we have not LAB and LAB. That's a contradiction. The KAB branch closes because we have not KAB and we have KAB here. Okay, on the right branch, we have not LAB and LAB. So this one branch on the right side closes, but on the right side, we have not KAB, LAB, and KAB. We don't have any issues with this. This branch is open. Not only is it open, but we've used every single thing that we can so far in our tree, except for just little literals here. So, because this is open, we can say that this is not a valid argument if it was an argument, but this was an entailment question. So this is an example of not having entailment because we have one open branch. Now, we could try some other strategies, but no matter which strategy we try, we're going to end up with the same problem. Because if we were to do, say, for example, let's just change this end of the tree here. Let's just say, what if we did a tree where we ended up with LBA arrow KBA? Then we would get not LBA on the left or KBA on the right. This side on the right would close, but we would still have an open branch on the left. So this is not valid, this is not an entailment, and this was probably the hardest one of all, because it really looks like you would have entailment here. If we have LXY, then we have KXY, entails that if we have LXY, then we have KXY and KYX. And you would think this because, oh, it's just taking everything in the universe and we could just flip these two around and this would be fine, but it turns out it does not entail. So if you have any questions, leave them in the comments below, or I'm sure someone can answer them. Maybe I'll be able to answer them, however it turns out. So thanks for watching, and like, comment, all that stuff helps a lot.